What if the world you can see and touch is not the fundamental version of reality, but a kind of averaged-out approximation of something underneath that operates by completely different rules? Not a philosophical provocation, not a thought experiment, a description of what the experimental record actually shows. Everything you have ever touched, every surface that has ever felt solid, every object that has ever cast a shadow, all of it is built from a layer of reality where the rules you use to describe the world simply stop working, where particles exist in multiple places at the same time, where two objects separated by the width of the universe can share a state that responds instantaneously to what happens to either one, where empty space is not empty, where a particle's properties do not exist until something measures them. Here is what makes that uncomfortable. We are not speculating. The experiments have been run. The predictions have been confirmed to a precision that no other scientific theory in history has matched. We know this layer exists. We can calculate its behavior with extraordinary accuracy, and we still do not fully agree on what it actually is. That is the tension this investigation is built around. Not whether quantum mechanics works. It works. The transistors in every device you own operate because physicists understood quantum behavior well enough to engineer it. The question is what the theory is telling us about the nature of reality itself, what actually exists at that level, not what the textbook summary says exists, what the physics, taken seriously, actually implies. Before you can understand why that question is so difficult, you need to understand one thing about the quantum realm. It is not small-scale classical physics. That is the mistake most people make when they first encounter it. The assumption is that atoms are just tiny versions of the objects we already know, that electrons orbit nuclei the way planets orbit a star, that everything down there works the same way it does up here, just smaller and faster. That picture is wrong, not approximately wrong, fundamentally wrong. The rules that govern matter at quantum scales are not a refinement of the rules that govern matter at human scales. They are a different set of rules entirely. And the world we experience is not what those rules naturally produce. It is what those rules look like after an enormous number of quantum systems interact with each other, and the quantum strangeness averages out into something our brains can navigate. What does that strangeness actually look like? A particle fired at two openings will pass through both simultaneously and interfere with itself, producing a pattern on the screen behind it that only makes sense if it traveled both paths at once. Measure which path it took and the interference disappears. Not because the measurement physically disturbed the particle in some correctable way, because the information exists. The universe responds to the availability of information, not just to physical contact. Two particles can become entangled such that measuring one instantly determines the state of the other, regardless of the distance between them. Einstein called this spooky action at a distance and spent years trying to explain it away. He was wrong. The experiments have confirmed it. Pace is not a barrier at the quantum level in the way it is at ours. And then there is the vacuum. Empty space, in quantum mechanics, is not empty. It is a seething baseline of field fluctuations, a ground state that is never zero, producing effects that are measurable in laboratories right now. Something is happening in nothing. That is not a metaphor. This is what the physics implies, not what a science fiction writer invented, not what someone proposed without evidence. What comes out of the most tested, most predictively accurate theory ever constructed when you read it carefully and take it seriously. The quantum realm is not a smaller version of the world you already know, and that difference is the most important thing physics has ever discovered. Every atom in your body is built from particles that were identified one by one over the course of a century, and the final list is stranger than anyone expected. Not one fundamental particle, not a handful. 17 distinct entities, sorted into categories, each with specific properties that determine everything about how matter behaves. And when physicists finished that list and called it the Standard Model, what they had actually done was locate the bottom of matter. Not approximately, not tentatively. They found the actual flaw. That is worth pausing on. For all of human history, the question of what things are made of sat open. And then, over about 100 years of increasingly violent experiments, we answered it. Here is what we found. Start with the quarks. 6 of them: up, down, charm, strange, top, and bottom. Those names are not descriptive of anything physical. They are labels, placeholders for properties that have no analog in the world you can see. Quarks are never found alone. Quantum chromodynamics, the theory governing the strong force, makes isolated quarks essentially impossible. Pull two quarks apart, and the energy you put in creates new quarks before they separate. They come in groups. A proton is two up quarks and one down quark, bound together by the strong force. A neutron is two down quarks and one up. Every nucleus in every atom in the observable universe is built from those two combinations. 6 quarks, and the useful ones for building matter are 2 of them. The other 4 are unstable, heavier, and exist only briefly under extreme conditions before decaying into something lighter. Now the leptons. 6 of those as well. The electron you already know. Then the muon, which is essentially a heavier electron. Same charge, same behavior, roughly 207 times the mass, and no known reason for existing. The tau particle is heavier still. Each of those 3 has a corresponding neutrino, which carries no electric charge and almost no mass and passes through ordinary matter essentially without interacting. Billions of neutrinos are moving through your body right now. They are real particles. They are part of the standard model, and they interact with matter so rarely that the entire Earth is nearly transparent to them. That is not a measurement artifact. That is what they actually are. Here is the part that most explanations skip over too quickly. Forces are particles too. That is not a loose analogy. It is the literal claim of the standard model. When 2 electrons repel each other, what is actually happening is an exchange of photons, virtual photons, mediating the electromagnetic interaction. The photon is not just light, it is the carrier of the electromagnetic force itself. Every time a charged particle pushes or pulls another charged particle, photons are the mechanism. The strong force that holds quarks together inside protons is carried by gluons, 8 of them, each with different combinations of what physicists call color charge. Gluons bind quarks so tightly that the mass of a proton is mostly the energy of those gluons, not the quarks themselves. What is mostly gluon energy. The weak force, responsible for radioactive decay, is carried by the W and Z bosons, massive particles, discovered at CERN in 1983, which confirmed a prediction that the electromagnetic force and the weak force are the same force at high enough energies. One force, 2 different faces depending on the energy scale. That unification is one of the most striking results in the history of physics. Then there is the Higgs. This one requires sitting with. Particles do not inherently have mass. That is not a simplification. Mass is not a property baked into particles the way charge is. Instead, there is a field, the Higgs field, that permeates all of space everywhere in the universe. Particles acquire mass by interacting with it. The stronger a particle's interaction with the Higgs field, the more massive it is. The photon does not interact with the Higgs field at all, which is why it has no mass and travels at the speed of light. The top quark interacts with it strongly and is the heaviest fundamental particle we have found. In 2012, the Higgs boson, the excitation of that field, the particle associated with it, was detected at CERN after a search spanning 4 decades. That detection confirmed the mechanism by which matter has mass, not a metaphor, the actual mechanism. And it points towards something that should be genuinely unsettling. The properties of the particles you are made of are not intrinsic to those particles. They emerge from the field they move through. What does that tell you about what matter fundamentally is? It tells you that the solid, definite, weighty stuff of the world is downstream of something more abstract. Properties arise from interactions with fields that exist everywhere and were present from the earliest moments of the universe. Here is my position on that. Most people, when they hear the word atom, still picture something with a hard center and electrons orbiting around it like a small solar system. That picture is not even approximately correct. The actual picture involves particles whose properties depend on which fields permeate space, bound together by the exchange of other particles, sitting mostly in empty space, with mass that isn't really theirs. The Standard Model is a precise, counterintuitive, experimentally verified description of what matter actually is at this level. And it is not finished. Neutrinos have mass, small mass, but mass, and the Standard Model in its original form predicted they should be massless. Dark matter, which accounts for roughly 27% of the total energy content of the universe, is not in the Standard Model at all. Gravity, which you experience every second, has no quantum description that fits inside it. The Standard Model is the most precisely tested theory in the history of science, and it is also, provably, incomplete. In 1801, Thomas Young fired a beam of light at a card with two narrow slits cut into it, and what appeared on the screen behind it should not have been possible. Two slits. You would expect two bright lines on the screen, one for each slit. That is what a stream of particles would produce. Bullets through two holes make two clusters on the wall behind them. Clean, predictable, classical. What Young got instead was a series of alternating bright and dark bands spread across the screen. Not two bands, many. A pattern that only makes sense if light is a wave, not a collection of particles. Two waves spreading out from the two slits, overlapping, reinforcing each other where their peaks aligned, cancelling where a peak met a trough. An interference pattern, the mathematics of waves, visible on a screen, produced by something everybody had been treating as particles of light. That result was disturbing enough on its own, but it was only the beginning. A century later, physicists started firing electrons at the same setup. Electrons are not light, they are matter. They have mass, charge, definite properties. They are, by every classical definition, particles. So here is what you would predict. Two slits, two clusters on the screen, the same result as bullets through holes. What they got was the same interference pattern Young saw with light. Electrons, matter, physical objects with mass, were behaving like waves. The field spent years arguing about what this meant. Was it some artifact of the equipment? Was it electrons repelling each other, somehow producing the pattern collectively? Those explanations were tested. They failed. Here is where it gets genuinely difficult to sit with. Physicists ran the experiment with one electron at a time. Fire an electron. Wait. Fire another. Wait. Each electron hits the screen at a single point, like a particle. Dot by dot, the screen fills up, and after enough electrons, the same interference pattern emerges. Single particles, fired one at a time, with nothing else in the apparatus to interact with, collectively building a pattern that requires each particle to have passed through both slits simultaneously. What does that tell you? Each electron is not choosing one slit. It is going through both, not half of it through each. The whole thing through both, at once, interfering with itself. That is what the pattern requires. That is the only explanation the math supports. Now here is the part that breaks the experiment open completely. Scientists designed a way to check. Place a detector at the slits, something that can register which slit each electron passes through without physically stopping it. Just a measurement. Just information. The electron still makes it through. You still get dots on the screen, but the interference pattern is gone. Two clusters. Particle behavior. Classical. The moment you have the information about which slit the electron used, the wave behavior disappears entirely, not partially disrupted. Gone. The setup had not physically altered anything about the electron's path. The detector was not blowing air at it or deflecting it with a magnetic field. The only thing that changed was whether the information existed. That is worth sitting with. The universe is not responding to physical disturbance. It is responding to whether the information is available. When no one can know which slit the electron used, it behaves as if it used both. When the information exists, even if no one looks at it, it behaves as if it used one. The pattern doesn't depend on whether a conscious observer checks the result. It depends on whether the information is encoded anywhere in physical reality. Einstein spent years insisting this could not be right. He was wrong. The experiments kept confirming it. And the experiments are not limited to electrons. This has been replicated with photons, with atoms, with molecules containing dozens of atoms, objects large enough to see with certain instruments, still producing interference patterns when unobserved. still collapsing to particle behavior when measured. There is no calibration fix for this. There is no version of the setup where careful engineering makes the problem go away. This is what quantum systems do. Every time. Reliably. Precisely. The interference disappears exactly when the information becomes available and returns exactly when it doesn't. Here is my position on what this implies. This is not a measurement problem in the practical sense. It is not like asking a child if they broke the vase and changing their behavior by asking. Something deeper is happening. The act of the information existing, of the physical state of the universe encoding which path was taken, is the thing that determines how the particle behaves. Reality at the quantum level is not simply unknown to us. It appears to be genuinely indeterminate until the conditions exist that would allow it to be determined. The question the double-slit experiment leaves you with is not one physicists have resolved by finding better instruments. Before measurement, the electron has no single definite trajectory. The math that describes it, the wave function, assigns probability amplitudes to every possible path, both slits, every point on the screen, the entire range. The interference pattern is not a mystery about where the electron went. It is a direct physical consequence of the electron having gone, in some physically real sense, everywhere the wave function allowed. The pattern is the wave function made visible. What does that mean for the electron between the moment it leaves the source and the moment it hits the screen? Where is it? What is it doing? Is it a particle with a position we simply don't know? Bell's theorem and the experiments following it ruled that out, and we will get to that. Is it a wave that only becomes a particle when it hits something? That interpretation has its own problems. Every major answer to this question carries consequences that are at minimum philosophically uncomfortable and in several cases physically radical. The only honest answer to what the particle is doing when nobody is looking is that physics, as currently written, does not tell you. The interference pattern in the double-slit experiment is not a metaphor for uncertainty. It is direct physical evidence that before measurement, the particle occupies multiple paths through space simultaneously. That is not an interpretation. It is what the mathematics requires and what every experiment confirms. The pattern only forms if the particle travels both routes. There is no version of events where it picks one path and still produces what we observe on the screen. So when physicists talk about superposition, they are not describing a gap in our knowledge. They are describing a feature of the particle itself. Here is the distinction that matters. Before measurement, the particle does not have a definite state that we simply haven't checked yet. It exists in a genuine combination of multiple states at once. The wave function, the mathematical object that describes the particle, assigns probabilities to all the possible outcomes simultaneously, and all of those outcomes are physically real until the moment of measurement forces one of them to become the actual result. This is not a claim that the universe is hiding something from us. It is a claim that definiteness itself does not exist until something selects it. That is what superposition means, and it is worth sitting with how strange that actually is. Erwin Schrödinger understood exactly how strange it was. In 1935, he constructed a thought experiment to make the problem impossible to ignore. A cat is sealed inside a box with a radioactive atom, a detector, and a mechanism that will release a poison if the atom decays. Quantum mechanics describes the atom as existing in a superposition of decayed and not decayed until it is measured. If that is true, the logic extends to everything connected to it: the detector, the mechanism, the poison, and eventually the cat. The cat should be, by the same reasoning, simultaneously alive and dead. Schrödinger did not propose this because he thought it was correct. He proposed it to demonstrate the absurdity of applying quantum superposition to macroscopic systems without explanation. What does that tell you about the state of the theory in 1935? The equation worked. Nobody agreed on what it meant. The obvious question superposition raises is this: if a particle can exist in multiple states at once, and particles make up everything, every molecule, every cell, every object you have ever touched, why does the world around you look so definite? Why do you never see a chair in two places, or a coin that is both heads and tails before you look? The quantum machinery is sitting underneath all of it. Why doesn't it show? The answer physicists arrived at is decoherence. When a quantum system interacts with its environment, other particles, photons bouncing off it, air molecules colliding with it, the superposition doesn't simply continue undisturbed. Those interactions entangle the system with enormous numbers of other particles, and the quantum interference effects that make superposition visible get washed out almost instantly. The larger and warmer and more connected to its surroundings an object is, the faster this happens. For a particle isolated in a controlled laboratory setup, superposition can persist long enough to measure. For a cat or a coin or any macroscopic object in a normal environment, decoherence happens in a time frame so short it is effectively instantaneous. The interference vanishes. What remains looks classical, definite, like tea. Decoherence is a real physical process. It is not a philosophical patch applied to make people feel better. The timescales are calculable, the predictions match experiment, and it explains why quantum weirdness doesn't visibly scale. But here is what decoherence does not do. It does not solve the measurement problem. It explains why superpositions become practically undetectable at large scales, but it does not explain why a specific outcome occurs. After decoherence, the mathematics still contains all the branches. It has not collapsed to one. Something else is required to get from a quantum system with many possible outcomes weighted by probabilities to the single definite result you actually observe. What is that something? That is the question nobody has fully answered. Some physicists treat collapse as a fundamental physical process that needs to be added to the equations. Others argue that collapse is an illusion, that every possible outcome happens in branching versions of reality that don't interact with each other. Others think the wave function was never a description of reality to begin with, just a tool for calculating what observers will see. These are not minor disagreements about interpretation. They are fundamentally incompatible claims about what actually exists. All of them reproduce the same experimental predictions. The experiment cannot separate them, and the question of which one is correct is not settled. What makes this particularly difficult is that the moment of measurement is not well defined in the mathematics. The Schrödinger equation, which governs how quantum states evolve over time, is perfectly smooth and deterministic. It does not contain a collapse. It does not contain a mechanism for selecting one outcome. It just evolves. The collapse appears when we compare the mathematics to what we observe, and the gap between them is exactly the size of the measurement problem. We insert collapse by hand, in effect, because we have to match what we see. But the theory does not tell us when or how or why it happens. There are systems today where superposition is not a theoretical abstraction. Quantum computers operate by maintaining qubits, quantum bits, in superpositions of 0 and 1 simultaneously. The computation runs on all states at once. The result extracted at the end is a single classical output. The gap between those two things, the quantum superposition and the classical readout, is exactly the gap the measurement problem has been pointing at for a century. We are now building machines that depend on it, which makes understanding it considerably more urgent than it used to be. 1 century after superposition was first formalized mathematically, the measurement problem, what actually happens when a quantum state collapses, remains one of the most contested questions in all of physics. The Heisenberg uncertainty principle is the most consistently misunderstood result in quantum mechanics, and the misunderstanding matters because the correct version is significantly stranger than the wrong one. Here is the wrong version, and you have almost certainly heard it. The idea goes like this. Particles are very small, and measuring them requires interacting with them, and that interaction disturbs what you are trying to measure. So when you try to pin down where an electron is, the act of measuring it knocks it around and scrambles its momentum. The uncertainty is real, but it is an engineering problem. Better instruments, more careful technique, smaller disturbances. The principle, in this version, is a practical limitation, a ceiling we have not yet reached. That version is wrong, not slightly wrong, fundamentally wrong. And the difference between the wrong version and the correct one is the difference between a technology problem and a statement about the architecture of reality. What Heisenberg actually showed is this. A particle with a precisely defined position does not have a blurry momentum because something disturbed it. It has an indefinite momentum because a definite position mathematically requires an indefinite momentum. These are not two separate properties that happen to interfere with each other during measurement. They are mathematically incompatible descriptions. You cannot have both at once because having both at once is not a coherent physical state. The precision in one is not traded against the precision in the other because of what we do. It is traded because of what the particle is. Here is where it connects back to what we covered on superposition. Particles in quantum mechanics are described by wave functions. Waves are extended things. A pure wave with a single precise frequency extends infinitely through space and has no definite location. It is everywhere and nowhere at once. A wave with a precise location, something sharply peaked at one point, is mathematically not a pure frequency at all. It is a superposition of many frequencies layered on top of each other. Now here is the key. In quantum mechanics, momentum is encoded in frequency. Specifically, de Broglie showed that a particle's momentum corresponds directly to the wavelength of its wave function. A single precise momentum is a single precise wavelength. An indefinite momentum is a mixture of many wavelengths. So a particle with a perfectly defined position, a wave function sharply concentrated in one spot, is mathematically required to be a superposition of many momentum values, not because anything disturbed it, because that is what a localized wave is. The mathematics forces it. Position and momentum are not two independent numbers attached to a particle that we happen to have trouble reading simultaneously. They are conjugate variables, mathematically linked, and the sharpness of one determines the spread of the other at the level of the wave function itself. What does that tell you? It tells you that the uncertainty is not in our knowledge, it is in the particle. There is no hidden layer of reality where the electron secretly carries a precise position and a precise momentum, and we simply lack the instruments to read both at once. That was tested. John Bell's work, which comes up in the next section, formally closed that door. Local hidden variables do not exist. The electron does not have a precise momentum we are failing to measure. It genuinely does not have one. Now extend this. Position and momentum are one conjugate pair. Energy and time are another. The shorter the time window you examine, the larger the uncertainty in the energy of a system during that window. This is not a separate principle layered on top of the first one. It is the same mathematics applied to a different pair, and the consequences are enormous. If you examine a small enough window of time, the energy uncertainty becomes large enough that the vacuum itself cannot be treated as having zero energy. Empty space, examined over short enough timescales, has energy fluctuations built into it. Not because something is happening to the vacuum from outside, because that is what the energy-time relationship requires. This is where vacuum fluctuations come from. This is the foundation of virtual particles. This is why the quantum vacuum is not empty, and why the Casimir effect, a measurable force between two metal plates in a vacuum, actually exists. All of it traces back to the same principle. Here is the position I want you to sit with. We are not talking about a situation where better technology closes the gap. CERN cannot fix this. A more sensitive detector cannot fix this. The uncertainty is not sitting between us and the particle. It is sitting inside the particle's own physical state. The properties we are trying to measure do not have simultaneous definite values to find. Asking what the precise position and momentum of an electron are right now is like asking what the precise north edge of a cloud is. The question assumes a precision the object does not possess. That is the part that never stops being strange. Classical physics assumes that physical properties are real, definite, and just waiting to be read. Quantum mechanics says that is not how the world is built at the scale where the actual building happens. Position, momentum, energy across short time windows, these are not properties a particle carries around independently of measurement. They do not exist in definite form until the act of measurement forces a definite value out of a distribution of possibilities. That is not a statement about what we can measure. It is a statement about what exists. In 1935, Einstein co-authored a paper intended to demonstrate that quantum mechanics could not possibly be a complete description of physical reality, and he used entanglement as the evidence. The paper, written with Boris Podolsky and Nathan Rosen, has been known ever since as the EPR paradox. Einstein was not confused. He was not unfamiliar with the math. He understood exactly what quantum mechanics was predicting, and that was precisely the problem. The prediction, to his mind, was absurd. Two particles interact, separate, and travel in opposite directions. You measure one. The other one, regardless of how far away it is, instantly reflects a correlated result. Not eventually, not after some signal travels between them. Instantly. Einstein called it spooky action at a distance, and he meant that as a condemnation. His position was direct. Either something is traveling between the particles faster than light, which relativity forbids, or quantum mechanics is missing something. Some hidden variable we have not found yet, carrying the answer in advance. That was the fork in the road. Hidden variables or faster than light influence. Einstein was certain the answer was hidden variables. What he did not anticipate was that the question was testable. In 1964, a physicist named John Bell produced a theorem that changed the entire argument. Bell showed that if hidden variables exist and are local, meaning they cannot influence each other faster than light can travel between them, then the correlations between measurements on entangled particles must fall below a certain mathematical limit, a specific number, a ceiling. Bell's theorem did not require you to accept any interpretation of quantum mechanics. It did not require philosophy. It required only that you run the experiment and compare the measured correlations to the limit his math specified. If the correlations stayed below the limit, hidden variables were viable. If the correlations exceeded it, local hidden variables were ruled out. That is an extraordinarily clean test for something this fundamental. Alain Aspect ran the experiment in 1982. The correlations exceeded Bell's limit, not slightly, not ambiguously. The results matched quantum mechanics and violated what any local hidden variable theory could produce. Aspect measured entangled photons under conditions designed to prevent any signal from passing between the detectors during the measurement, closing a loophole that earlier experiments had left open. The result held. It has been repeated hundreds of times since, with increasing rigor, closing additional loopholes one by one. The loophole-free Bell tests of 2015 addressed the final significant objections simultaneously. The answer has not changed. Local hidden variables do not explain the correlations. What Einstein called spooky action at a distance is not a gap in the theory. It is a feature of reality. Here is what that actually means. When two particles are entangled, their quantum states are not independent. The combined system is described by a single wave function. Measuring one particle does not reveal a pre-existing value that was always there. The measurement produces an outcome, and the correlated particle produces a matching outcome, and no mechanism traveling at or below the speed of light connects those two events. The correlations are too strong for any classical explanation. That is not an interpretation. That is what the experimental data shows. Some part of you may want to find a way around that. Physicists have spent 60 years looking. There is not one. So then the obvious question. If entanglement is instantaneous and real, why can you not use it to send a message faster than light? Here is where it gets precise. When you measure your particle, you get a random result. Spin up or spin down, with no way to control which one you get. Your partner measures their particle and gets the correlated result. The correlation is perfect. But you had no control over your outcome, which means your partner's result also appears random to them. Neither of you can encode information into the outcomes because neither of you chooses what the outcome is. You can compare notes after the fact using a classical channel and confirm the correlations. But that comparison travels at the speed of light or slower. The entanglement produces correlations you can only verify classically. The non-locality is real, but it does not give you a signaling channel. Relativity remains intact, and not because of a coincidence. The structure of quantum mechanics is built in a way that makes this exactly the case. What entanglement does allow is something called quantum teleportation, which is real and has been demonstrated in laboratories. It does not mean moving matter through space. What it means is this. You can transfer the complete quantum state of a particle to a distant particle using a combination of entanglement and a classical communication channel. The original particle's state is destroyed in the process. The distant particle takes on the transferred state. The classical channel is still required, so nothing moves faster than light. What teleportation demonstrates is that entanglement is a genuine physical resource. It is not just a statistical correlation you notice after the fact. It is something you can use, something that carries real computational and informational value. Quantum cryptography is built on this. Quantum computing depends on it. These are not theoretical applications waiting for future physics. They are being engineered now. But the deeper question is what entanglement tells you about space itself. In standard physics, the assumption is that distant objects are independent. What happens here does not instantly affect what happens there, and the distance between two locations is a real physical fact that limits interaction. Entanglement breaks that assumption without violating relativity, and that combination is uncomfortable. It means space does not fully separate entangled particles the way it separates everything else. Some physicists have pursued this seriously. The ER equals EPR conjecture, proposed by Juan Maldacena and Leonard Susskind in 2013, suggests that entangled particles are connected by microscopic wormholes and that the geometry of spacetime may itself emerge from patterns of quantum entanglement. That is not established physics, it is a research direction. But the fact that serious physicists are proposing that entanglement and spacetime geometry are two descriptions of the same thing tells you something about how far this reaches. Einstein's paper in 1935 was meant to close a door. What it actually did was identify the most important open question in the foundations of physics. The correlations are real, they are non-local, and the structure of space does not explain them. Some physicists now argue that entanglement isn't just a strange feature of quantum mechanics. It may be the mechanism by which spacetime itself is stitched together. Every second, inside the sun, protons that classically lack the energy to reach each other are fusing anyway, and the reason is quantum mechanics. The temperature at the core of the sun is roughly 15 million degrees Celsius, which sounds extreme until you calculate what it actually means for particle energy. It is not enough. Classical physics is unambiguous on this point. The protons moving around in that environment do not carry sufficient energy to overcome the electromagnetic repulsion between them. They should never touch, they should never fuse. And yet the sun has been fusing hydrogen for 5 billion years. What closes that gap is quantum tunneling, and it is worth understanding precisely why. In classical mechanics, a particle that lacks the energy to cross a barrier simply stops. It hits the barrier, it bounces back. It is a hard physical limit. The barrier height is a real energy threshold, and if the particle's energy falls below it, crossing is not possible. Full stop. Quantum mechanics does not work this way, and the reason comes directly from what was covered in the last section. Particles are not point objects with definite positions. They are described by probability waves, and those waves do not terminate cleanly at the edge of a barrier. They extend into it. They extend through it. On the far side of the barrier, the wave amplitude is reduced, but it is not zero. A non-zero wave amplitude means a non-zero probability of finding the particle there. And a non-zero probability, given enough particles and enough time, means it happens. That is tunneling, the actual mechanism. What is strange about tunneling is that it is happening constantly, at scales that affect your life directly. The transistors in every processor you have ever used depend on it. Modern chips pack transistors so densely that the insulating layers between components are only a few atoms thick. At that scale, electrons tunnel through the insulation whether the engineers want them to or not. Sometimes this is a feature. Flash memory stores data by trapping electrons that tunneled through a barrier, and the stability of that trapped charge is what holds the information. Sometimes it is a problem. As transistors shrink, leakage current from unwanted tunneling becomes one of the central engineering challenges in chip design. The electrons tunnel either way. Alpha decay works by the same mechanism. An alpha particle inside a nucleus is held in by the strong nuclear force, which creates an effective energy barrier. The alpha particle's energy is below the barrier height. By classical physics, it should stay inside forever. Instead, there is a probability amplitude for the particle to exist outside the nucleus, and eventually that probability resolves into a real detection event. The nucleus decays. The timing is probabilistic, which is why we describe radioactive decay with half-lives rather than exact decay moments. That probabilistic character is not a gap in our knowledge. It is the physical reality. The scanning tunneling microscope, developed in the early 1980s, uses the same effect to image individual atoms. A sharp metallic tip is brought to within a nanometer of a surface. At that distance, electrons tunnel across the gap between the tip and the surface, generating a measurable current. As the tip moves across the surface, variations in the tunneling current map the electron density of individual atoms. They are direct readouts of quantum probability amplitudes translating into electrical signals. The instrument works because tunneling is real and quantitatively predictable. Now look at what happened in 2025. John Clark, John Martinis, and Michel Devoret received the Nobel Prize in Physics for experiments conducted in 1984 and 1985. What they demonstrated was macroscopic quantum tunneling, a system not of one particle but of billions of particles, all acting together as a single quantum unit, tunneling as a collective. The superconducting circuits they built allowed a macroscopic degree of freedom, a current involving an enormous number of electrons, to behave quantum mechanically. The tunneling event involved the entire collective state of the system crossing an energy barrier that the system classically lacked the energy to cross. They measured it. The tunneling rate matched the quantum mechanical calculation. What that result closes is the argument that quantum behavior is somehow confined to the microscopic and that classical physics takes over at larger scales through some automatic process. It does not. Scale does not turn off the quantum mechanics. Under the right conditions, the collective state of a macroscopic system tunnels just as an electron does. Here is what tunneling forces you to accept about quantum probability. It is not a description of what we do not know. It is not a way of expressing ignorance about the particle's actual trajectory. The particle does not have a hidden classical path that we just cannot track. The probability wave is what there is, and what the wave predicts is what the universe delivers, including outcomes that classical physics declares impossible. The sun is generating energy through a process that should not happen. Your memory card is holding data through a process that should not happen. The nucleus of every radioactive atom in existence is decaying through a process that should not happen. They all happen because the wave says they can, and the universe listens to the wave. Tunneling is what happens when probability is not a description of our ignorance, but a description of what the universe actually does. The deepest version of what exists inside the quantum realm is not particles, it is fields, and the particles you learned about in school are what those fields look like when they're disturbed. That requires some unpacking. When quantum mechanics was first developed in the 1920s, it worked beautifully. It predicted energy levels, described atomic structure, explained the photoelectric effect. But it had a problem nobody advertised loudly in the textbooks. It was built around a fixed number of particles. Put 2 electrons in, get 2 electrons out. The particle count was conserved by assumption. Then you try to combine quantum mechanics with special relativity, and that assumption collapses immediately. Special relativity says energy and mass are equivalent. That means if you concentrate enough energy in a small enough region, you can produce new particles, matter out of energy. And the reverse is also true. Particles can annihilate and become pure energy. A theory that assumes a fixed particle count cannot handle a universe where particles are created and destroyed. Something had to give. What gave was the concept of particles as fundamental objects. That is the move that quantum field theory makes. Not a refinement, a replacement. The universe in this framework is not filled with particles. It is filled with fields. The electron field, the photon field, the quark fields. One field for each type of particle in the standard model. And these fields extend through all of space, everywhere, always. What we call an electron is not a tiny object sitting at a location. It is a localized excitation in the electron field. A ripple, a disturbance. The field gets kicked. And that disturbance behaves like a particle because it carries energy and momentum and travels as a coherent unit. But the field was there first. The field is always there. The particle is what the field looks like when something happens to it. Here is why that matters. In a particle-based picture, empty space is empty. No particles, nothing. In the quantum field picture, empty space is not empty and cannot be empty. The fields are still there. They pervade every region of space, including the regions where no particles are present. And here is the part that has measurable consequences. Every field has what physicists call a ground state, the lowest energy configuration it can occupy. In classical physics, the lowest energy state of a system is zero. Nothing moving, nothing fluctuating. In quantum mechanics, that is not allowed. The uncertainty principle connects energy and time the same way it connects position and momentum. A field with exactly zero energy at a precisely defined moment would violate that relationship. So the ground state of every quantum field carries residual energy. It fluctuates, even at absolute zero, even in perfect vacuum. The vacuum is not a passive backdrop for physics. It is an active, fluctuating structure. Is that actually true? Or is it a mathematical artifact? Here is the answer. Take two metal plates, place them extremely close together in a vacuum, millimeters apart, then micrometers, fractions of a micrometer. The plates will experience a measurable attractive force pushing them together. No charge on the plates, no magnetic field, no particles between them. The vacuum is pushing them. This is the Casimir effect, and it has been confirmed in laboratory measurements repeatedly. What is actually happening is this. The vacuum fluctuations of the electromagnetic field exist both between the plates and outside them. But between the plates, the geometry restricts which fluctuation modes can fit. Fewer modes between the plates than outside. The fluctuation pressure from outside exceeds the fluctuation pressure from inside, and the plates feel a net force. A force generated by the energy of empty space, measured with instruments, not calculated in a textbook as a hypothetical. That is what the quantum vacuum actually does. Now, virtual particles. This is where the popular science version diverges from the technical reality, and the divergence matters. You have probably heard that the vacuum is full of virtual particles constantly popping in and out of existence. Particle-antiparticle pairs spontaneously appearing and annihilating in fractions of a second. It is a compelling image. It is also not quite the right way to think about it. Virtual particles are not real particles briefly visiting from nowhere. They are a calculational tool. When physicists use perturbation theory to calculate how quantum fields interact, they expand the calculation as a series of terms, and each term can be represented graphically as a Feynman diagram. The internal lines in those diagrams are what we call virtual particles. They are bookkeeping entries in a mathematical expansion, not physical objects with trajectories. What those bookkeeping entries calculate, however, is real, the Casimir effect. The Lamb shift in hydrogen spectral lines, the anomalous magnetic moment of the electron, which quantum field theory predicts to 11 decimal places and experiment confirms to 11 decimal places. The effects are real. The virtual particles are the ledger entries used to calculate those effects. Here is the question this raises. If every quantum field has a non-zero ground state energy, and there are roughly 20 fields in the standard model permeating all of space, then the total energy density of the vacuum should be calculable. Quantum field theory gives you a prediction. You can compute it. And then you look at what the actual energy density of the vacuum appears to be from cosmological observations, from the measured expansion rate of the universe, from the behavior of space-time at large scales. And the two numbers do not match, not slightly, not by a factor of 2 or 10. The theoretical prediction is larger than the observed value by approximately 120 orders of magnitude. That is a 1 followed by 120 zeros. This is not a problem hiding at the edge of precision measurement. It is the most catastrophic mismatch between a theoretical prediction and an experimental result anywhere in science. What does that tell you? Either the calculation is wrong in some systematic way nobody has identified, or there is a cancellation mechanism that reduces the vacuum energy by 120 orders of magnitude and leaves behind exactly the small residual we observe, and that cancellation would require an explanation nobody has. Both options are uncomfortable. Neither has been resolved. The theory that explains the Casimir effect predicts the electron's magnetic moment to 11 decimal places and underlies every particle physics calculation done in the last 50 years, simultaneously predicts a vacuum energy density that is off by a factor that has no analog anywhere in the history of quantitative science. That gap has been sitting in the literature since the 1960s, and it has not closed. The vacuum energy discrepancy, 120 orders of magnitude between prediction and observation, is not a rounding error. It is the largest gap between theory and reality in the history of physics. Here is the most uncomfortable fact about quantum mechanics. The experiments are finished, the predictions are confirmed to extraordinary precision, and physicists still cannot agree on what the theory means. That is not a minor academic dispute. That is a century of verified predictions sitting on top of a foundation that nobody can fully describe. The mathematics works. The technology works. The interpretation, what is actually happening when a quantum system does what it does, is genuinely unresolved. And the reason that matters is this: different interpretations are not different explanations for different experimental results. They make identical predictions, every single one. The experiment cannot separate them, which means the choice between them is not a scientific choice in the ordinary sense. It is a choice about what kind of reality you are prepared to accept. Start with Copenhagen. This is the oldest interpretation and still the most commonly taught. The core position is something close to this. The wave function is a calculational tool. It tells you the probability of getting a particular result when you measure. Asking what the particle is actually doing before you measure it is not a deep question. It is a meaningless question. Stop there. Do the calculation. Get the answer. This position is sometimes called shut up and calculate, and it has a certain hard-nosed appeal. It keeps physicists focused on what the theory can actually produce rather than philosophical tangents. The problem is that it refuses to answer the most obvious question the theory raises. If the particle has no definite state before measurement, what exactly happens at the moment of measurement? Copenhagen does not say. It draws a line between quantum and classical, treats the act of measurement as something outside the theory's jurisdiction, and moves on. That gap has bothered physicists since the 1920s. Many world steps directly into that gap and fills it with something most people find even harder to accept. The wave function never collapses. Ever. When a measurement occurs, the universe branches. Every possible outcome happens. There is a version of the universe where the detector clicked and a version where it did not, and both are equally real. You, the observer, end up in one branch. But the other branch exists. All the branches exist. All of them, every time. The ontological cost of this is staggering. Many worlds does not add hidden mechanisms or extra variables. It adds worlds, a literally uncountable proliferation of parallel realities, generated continuously by every quantum event everywhere in the universe. Others find it the most extravagant hypothesis in the history of science, c.e. Pilot wave theory, developed by David Bohm in the 1950s, takes a different approach. Particles have definite positions, always. There is no superposition of actual states, no uncertainty about where things are. What guides the particle is a real physical wave, the pilot wave, that propagates through space and determines how the particle moves. The wave goes through both slits in the double-slit experiment. The particle goes through one. The wave's interference pattern then guides where the particle ends up, producing the observed distribution. This reproduces every quantum prediction without superposition, without collapse, without branching universes. Here is the catch. The pilot wave is explicitly non-local. The wave that guides a particle here is affected instantaneously by what happens to an entangled partner on the other side of the galaxy. Pilot wave theory does not hide the non-locality the way Copenhagen does. It puts it directly into the structure of the theory. For others, it is a feature, not a flaw. At least it tells you what is actually there. Then there are interpretations that locate the quantum state not in the world, but in the observer. Relational quantum mechanics holds that quantum states are not absolute properties of systems. They are properties relative to other systems. A particle does not have a definite state, period. It has a definite state relative to you, which may be different from its state relative to someone else. Cubism, quantum Bayesianism, goes further. The wave function represents an agent's beliefs about what they will experience when they make a measurement. It is not a description of external reality at all. It is a bookkeeping tool for a particular observer's expectations. When the wave function updates after measurement, that is not a physical event happening in the world. That is the agent updating their beliefs. Both of these positions sidestep the measurement problem entirely by relocating the quantum state inside the relationship between observer and system, or inside the observer's head. Here is what connects all of them. Every interpretation is an attempt to answer the measurement problem. When a quantum system is in superposition and a measurement occurs, something changes. A range of possible outcomes becomes one actual outcome. What is the physical process by which that happens? Is it collapse? A real physical transition with no mechanism described? Is it branching? Is it that the question itself is malformed? A century of quantum mechanics has not answered this. The experiments confirm the probabilities. They do not tell you what happens to produce one result instead of another. That absence is not a gap waiting to be filled by the next experiment. It is a structural feature of the theory as currently written. My position is that this should be stated plainly and oft. We are not one measurement away from resolving this. We may need something that does not look like quantum mechanics at all. Every interpretation of quantum mechanics is a different answer to the same question. What is real when nobody is looking? And after a century, the question is still open. Everything described in the last hour has a practical consequence, and the industry being built on top of quantum mechanics right now is not science fiction. It is engineering. Start with quantum computing, not the version in press releases, the actual version. A classical computer processes information in bits. Each bit is a 0 or a 1. A qubit, by contrast, can exist in superposition, 0 and 1 simultaneously, until measured. That means a quantum computer working through a problem isn't checking one solution at a time. It's exploring multiple paths through a solution space at once. Add entanglement, and qubits become correlated in ways that have no classical equivalent. The computational relationships between them can't be replicated by stringing together more classical processes. That's not a claim about speed. It's a claim about a fundamentally different kind of computation. Where quantum computers currently stand is worth being honest about. They exist. They work. IBM, Google, and others are running real quantum hardware. But for most practical problems, a classical computer still outperforms them. The threshold where quantum hardware becomes broadly superior, what the field calls quantum advantage, has been demonstrated for specific narrow tasks and not yet for general use. That gap is closing. It has not closed. Quantum cryptography is a different story, and a cleaner one. When two parties communicate using entanglement-based protocols, any interception collapses the quantum state. The eavesdropper doesn't get a copy of the message. They leave a detectable mark on it. The security isn't based on computational difficulty the way classical encryption is. It's based on physics. That's a qualitatively different guarantee, and the infrastructure to use it is already being built. Now here is where the unanswered part starts. Quantum mechanics and general relativity are both extraordinarily successful theories. They are also, mathematically, incompatible. At the scales where both should matter, the interior of black holes, the first moments of the universe, the two frameworks produce results that cannot both be right. Nobody has resolved this. It is the central open problem in theoretical physics. Why does the universe look classical at large scales when everything underneath it is quantum? Decoherence gives a partial answer. It doesn't give a complete one. The quantum vacuum carries an energy density that quantum field theory predicts to be roughly 120 orders of magnitude larger than what we observe. That is not a minor discrepancy. That is the largest mismatch between theory and measurement in all of science, sitting unaddressed in the literature. And then the deepest question, which nobody can currently answer, is quantum mechanics the bottom layer, or is there something underneath it that quantum mechanics is an approximation of, the way Newtonian mechanics is an approximation of relativity? We built the most accurate scientific theory in human history. It describes a layer of reality where none of our intuitions apply, and we still don't know what it's actually telling us about what exists.